Uh, Good afternoon, everybody. I'm Bassam Moujalled, a researcher in building energy efficiency and indoor environmental quality. I work for Cerema, which is a French public body in support of national and local authorities in the field of sustainable development. And the following presentation is about the in situ assessment of long-term and mid-term building airtightness durability. For the introduction, I will be quick as the subject was already introduced by Valérie in the beginning of this webinar, and also Wolf has presented the context of the durability of building airtightness. Today there is a low expertise available on the durability of building airtightness and how it evolves over time in midterm and long term. The French research project Durabilitaire, which ended in October 2019, aimed at improving our knowledge on the variation of buildings' airtightness through on-site measurement campaign and accelerated aging in laboratory controlled conditions. The literature review done by Valérie and that was presented in the beginning of this webinar showed that the air permeability in real buildings can vary significantly, especially in the first years of the building. In this presentation, I will focus on the results of the second task of the project, which deals with the quantification and qualification of the durability of building airtightness through field measurements at midterm and long-term scales. The work done concerning the laboratory measurements will be presented during the webinar in February. In order to evaluate the durability of building airtightness in real conditions, we have conducted a midterm and long-term measurement campaigns based on two samples of single detached low-energy dwellings. For both samples, all dwellings were measured upon completion, and treatment of airtightness was well known in order to reduce uncertainties about main factors impacting the building airtightness. The measurement upon completion will be referred as measurement N0 in this presentation. And regarding the midterm campaign, which aimed at investigating the yearly evolution of building airtightness over a 3-year period, we have selected a sample of 30 new single-detached low-energy houses, all measured upon completion, and the airtightness of each dwelling was measured once per year over the 3-year period of the project. These measurements are referred as N1, N2, and N3 respectively. Besides, 5 buildings of the sample were measured twice per year in order to investigate the impact of seasonal variations, and for 6 dwellings, the airtightness of an installed window were measured once per year over the 3-year period. For the long-term campaign, which aimed at characterizing the evolution of building airtightness over a longer period, around 5 to 10 years, a second sample of 31 existing houses was selected, and all were measured upon completion. The dwellings were constructed during the last 10 years. The airtightness of each dwelling was measured once, and this measurement is referred as measurement NX in this presentation. Regarding the measurement protocol used in this study, it was based on the literature review that was conducted by Valérie and that was presented earlier by Valérie. We have used mainly the standard ISO 9972 and its French implementation guide. In addition, we have used requirements for the measurement conditions in order to reduce uncertainty due to measurement procedure. For example, all measurements were performed under the same conditions as the first measurement upon completion, both in pressurization and depressurization, with the same building preparation, same testers, same measurement devices. Detailed qualitative leakage detection were performed at each measurement, and questionnaires for occupants were filled at each measurement in order to identify their action on the building envelope, like drillings to fix furniture or replacement of components. At the total, 140 measurements of building airtightness were performed for midterm and long-term samples. I will present now the main results of this study, and I will start by this figure, which shows the distribution of buildings according to the year of construction. For the midterm sample showed in blue, dwellings were constructed mainly in 2014 and 2015, and the first year measurements, N1, were performed from 1 to 3 years after the measurements N0, with an average time span of 1.7 years. Indeed, the measurements were delayed due to difficulties in finding occupants willing to be involved in a 3-year-long measurement campaign. And therefore, in order to compensate this delay, the average time spans between the following measurements were slightly lower than 1 year, with 0.7 years between N1 and N2 and 0.9 years between N2 and N3. For the long-term sample showed in orange, dwellings were constructed between 2009 and 2015, and all measurements and NX were conducted in 2017 from 3 to 8 years after the building completion and with the measurement N0, and with an average time span of 4.6 years between N0 and NX. Only 9 houses were older than 5 years in this sample. As for midterm sample, we had difficulties to find houses fulfilling selection criteria with volunteer occupants. Now, this figure shows the distribution of buildings according to the main material and type of air barrier. For midterm sample showed in blue, all houses are built of masonry with interior insulation, and the air tightness is treated by the same way through plasterboards and mastics at the inside facing of the walls, referred as air barrier C on this figure. For the long-term sample showed in orange, also the majority of houses are built of masonry with interior insulation. We had also 6 wooden houses. The air tightness of masonry houses is mainly ensured by coating on the masonry, called air barrier B, and the air tightness of the wooden houses is ensured by the vapor barrier, called air barrier A. Now I will present the results of the air permeability measurements expressed here according to Q50, which is the air leakage rate at the reference pressure difference of 50 Pascal, which is more reliable than the pressure at 4 Pascal as mentioned earlier by Valerie. This figure shows the box plots of the air leakage rate Q50 for different measurements of the midterm sample. For the measurements, however, for the measurements N0, tests were performed by either pressurization or depressurization, unlike the other measurements N1, N2, and N3, where tests were performed by both pressurization and depressurization. So for the midterm sample, we can observe a significant increase in the mean air leakage rate Q50 between the measurement N0 and N1 by almost 60 cubic meter per hour, and which represent an increase by 18%. After the measurement N1, we observe a stabilization of Q50 at N2 and N3. Regarding the long-term sample, this figure shows also the box plots of the measured air leakage rates at 40 Pascal. As for the long-term midterm sample, we observed similar results with a significant increase in the mean air leakage rate Q50 between measurement N0 and NX by around 68 cubic meter per hour, which represents an increase of 20%. Now, if we look at the variation of the evolution in air leakage rate Q50 against the time span between measurements on this figure, we can see a lack of correlation between the evolution in Q50 and the age of the houses for both midterm and long-term samples. Therefore, the air permeability does not seem to change with the age of the building. It varies mainly during the first 2 years, between N0 and N1. of the building and then stabilizes as observed in the literature review. Variations during the first 2 years may have several origins, including the actions by the occupants when they move in the building, like installing furniture or picture frames, and also the first heating of the buildings. In order to go further in the understanding of the variation of building airtightness, we have examined the evolution of air leakage rate Q50 regarding buildings' main characteristics and modifications by occupants. This figure shows on the left y-axis the relative gap in Q50, and on the right y-axis the evolution in Q50 between various measurements for all houses of the midterm sample. The houses on the x-axis are sorted in ascending order of the evolution in the air leakage rate Q50, and they are classified into 4 categories depending on the evolution in Q50, with 5 houses with significant decrease in Q50, 13 houses with no or little variations, 6 houses with moderate increase of Q50, and finally 5 houses with strong increase of Q50. And among the different factors analyzed, we mainly identified the following factors. First, the number of levels. We are generally observing an upward trend to the air leakage rate for the 2-story detached houses shown in gray on this figure. For these houses, it seems the air tightness to more deteriorate than 1-story houses. This can be explained by the structural movement due to foundation settlements. The evolution of the air leakage rates also seems to be sensitive to the type of roof. If we look in particular at the 2 houses with exposed wood frame on this figure, for dwelling number 6 in the red box, the air tightness has become, the house had become much leakier, with an increase by 180%, mainly because of leakages appearing at the junction between the wood and the plasterboard due to the shrinkage of mastic. While for the dwelling number 19 in the green box, the air tightness has remained almost stable. Knowing that both houses are tightened by the same method, the conditions of implementation of the air barrier seem to have an impact on the durability of the air tightness. And finally, we observed that the air tightness of the 6 wooden houses of the long-term sample, shown in yellow on this figure, the air tightness remained stable and even improved for 2 wooden houses. It is interesting to note that laboratory testing has come to the same conclusion on wood structure. This may be due to the expansion of wood with the humidity that would expand the wood and therefore reduce leakages. Regarding the evolution of leakages, well, this figure shows the evolution in the number of observed leakages between various measurements. On the left y-axis, you can see the evolution in the number of leakages for the midterm sample. For different categories of leakages, the categories are shown for category B to category H. And on the right y-axis, you can see the evolution in the air leakage rate Q50. The houses on the x-axis are sorted in ascending order of the evolution in Q50. First, you observe an significant increase in the number of leakages for doors and windows, for also the electrical components, for the penetrations through envelope, and also for the junctions between walls and doors or windows. However, the multiple linear regression that has been performed has shown that the evolution in Q50 was not correlated with the evolution in the number of leakages. As you can see on this figure, for some houses with a decrease in Q50, like the house number 10 in the blue box, there is an increase in leakages equivalent to houses with a strong increase in Q50, like the house number 6 in the red box, for example. Therefore, a thorough leakage location detection is not useful as long as it does not quantify leakages for the analysis of the on-site durability. Thus, new methods are needed to detect and quantify leakages. This will bring us now to the main conclusion of this study. The durability of building airtightness of low-energy single-detached houses was assessed through two field measurement campaigns at midterm and long-term scales. The results showed the same evolution of the airtightness at midterm and long-term. Indeed, both samples show the same mean increase in the air leakage rate Q50, around 20%. Also, there is a lack of correlation of this increase with the age of construction. And the air tightness deteriorates mainly during the first 2 years, and then it stabilizes. Results show also a significant increase in the number of observed leakages. However, no correlation was observed with the variation in air leakage rate. Several factors regarding building main characteristics and the modification of envelope were analyzed in order to explain the variation in air tightness, and results show no impact for constructor, type of barrier, of floor, of heating, and specific HVAC equipment. Also, no impact for seasonal variation, and the air tightness of wood houses tend to stabilize or even improve over years. Also, the two-story houses seems to deteriorate more than one-story houses. In this project, gathered information has explained a part of the evolution in the air permeability. However, neither leakages detection nor building characteristics are correlated with the observed evolution in the air leakage rate. Therefore, there are probably other factors not considered in this study which have an impact on the durability of the air tightness, such as the environmental conditions as mentioned earlier by Valerie, like the temperature or the dustiness, when the air barrier is implemented. So it would be interesting to investigate such parameters in future studies. Thanks, and thank you for your attention, and the detailed results and the final reports and articles of this project can be found on the website of the project. And I will be happy now to answer your questions, or during the webinar, or eventually by sending an email later.